before we learn about half adder and full adder, first we'll see what binary addition and how it works. So a binary addition is basically same as the decimal addition, but but the thing is, it's a binary system is a base 2 system, so it has just two digits, 0 and 1. So in a base 10 system, if you do addition, uh, we know that the sum overflows when it crosses 9. We carry over the next digit, we carry over the 1 to the next digit and then add it. So similarly, there are just two digits in the base 2 system, so the 0 and 1. So if the sum overflows 1, we'll carry to the next place while adding. So everything is same. Everything in binary addition is same as what we do in decimal addition. But the only difference is it has just two digits, 1 and 0. We'll see some simple properties of the properties of binary addition. These are like really simple properties, uh, there shouldn't be much trouble in understanding it. So the first one is 0 plus 1 equals 1 in binary addition, similar to the normal one, and 1 plus 0 is 1. But note that the thing is the plus here is not the logical OR operator. Uh, it's not the logical OR operator. It's the operator used for binary addition. So you should not get confused on that. So the next one is 0 plus 0 equals 0. And in the next one, we can see that 1 plus 1 equals 0. So if we add 1 plus 1, we'll get 1 0. That is 2 in decimal. So if we keep 0 in that place, and while doing binary addition, we usually we shift that 1 to the next place. We take it as a carry. So yeah, similarly, we can understand the last point also. So 1 plus 1 plus some carry 1. It equals 1. So first, when we do 1 plus 1, we'll get 1 0. So 0 will be in that place, and then 1 will move to the next place as the carry. So if in that place, if there is some carry already present from the previous digit, we also some carry or 1 already present from the previous digit, we also add it, so we'll get 1 again. So these are the rules for binary addition. Now we'll move on to we'll talk about what a half adder is. So half adder is basically a circuit with two inputs and two outputs. From the truth table, we can see that the circuit has two inputs, X and Y, and it has two outputs, C and S. C stands for carry and S stands for sum. So this X and Y represent the add-in and the argon and the add-in bits. So in the previous page, we saw these rules as 0 plus 1 equals 1, 1 plus 1 equals 0 plus carry over 1. So these inputs, we can designate them using the variables X and Y. And then the outputs, the sum, the outputs can be designated using a symbol C and S. So we're basically doing the same thing over here. And so there are two inputs, X and Y. Each input can be either 0 or 1. So there are 4 possibilities in the truth table. Now we'll write the truth table of half adder. When both the inputs are 0, 0 plus 0 equals 0. So the sum is also 0, carry is also 0. So you can see C is 0 and S is 0 here. When X equals 0 and Y equals 1, when one of the bit is 0 and another bit is 1, the sum is 1, but the carry is 0 because it hasn't yet overflowed into the next digit. So the carry is still 0 and the sum is 1. So similarly, we can see that when X equals 1 and Y equals 0, the carry is 0 because we still haven't overflowed to the next digit, so the carry is still 0 and the sum is 1. When both X and Y are 1, the sum is 0. Um, as 1 plus 1 equals 1 0, we keep the zeros in the same place and we'll move the 1 in the next place. We'll move the 1 to the next place as a carry. So the sum here is 0 and the carry is 1. We'll actually go to Logisim. We'll implement this and see how the circuit comes out to be. I hope my Logisim screen is visible.
Yeah, it is.
Okay. First, in order to create any combination circuit, we can go to this window. We can click this combination analysis option. Okay, so we can add inputs and outputs over here. We can add the input variables over here. So the inputs in our truth table are x and y. So we can just add x and add y. So we'll keep both these inputs are 1 bit because they can either take 0 or 1. So they are 1 bit input variables. And then moving on to the output column, we have two outputs over here, the sum and carry. So we'll name C for we'll keep C for carry and S for sum. So both these inputs are 1 bit because they can either take 0 or 1. We just keep these inputs as 1 bit inputs. Yeah. And then we can move to the truth table. So it automatically generates us this table with all the possibilities 0, 0, 0, 1, 1, 0, 1, 1. So we just have to click on these columns. We have to edit this to get the required truth table for the half adder. So when both these inputs are 0, sum is 0 and the carry is 0 and sum is 0. So when one input is 0 and one input is 1, the sum is 1 and the carry is 0. And same case for next entry also. So next, when both of these inputs are 1, the sum is 1 and the sum is 0 and then the carry is 1. Okay, so now if we move to this expression column, we can see that by it automatically generates us all these expressions for us: c equals xy, x equals x dash y, and plus xy dash. So it automatically generates this k maps. It automatically minimizes it. We just have to give the inputs. We just have to give the input variables, the output variables, and enter its truth table. So it basically does everything for us. Now, now if we click build circuit, uh,
Santosh,
yeah,
your PPT is not visible.
uh, I'm actually sharing Logisim. Yeah, actually,
Okay, okay.
No, the other window which you have opened is not it. I think you have to share your entire screen
okay, okay.
instead of sharing a window.
I'll stop sharing and do it again. So,
Yeah.
okay, now is my screen visible?
Like, is there any other screen open along with this?
I
That
shared the whole window.
okay, okay. Yeah, now it's visible.
It's visible, right? Okay, so we'll do this part once more. We can go to the combination analysis in the window. Yeah, so basically what I did was, I hope this window is visible.
Yes, now
So
it is.
basically what I did was, I clicked this add a new variable. I added two input variables x and y, which are the inputs in the half adder. And similarly, I clicked this option. I added two output variables. I added two output variables c and s, where c stands for carry and s stands for sum. So on the next in the next stage, the next tab, it automatically generates as a table xy 00011011. So we can just edit this right hand part to whatever our truth table is. So I've just edited these entries and created the truth table for the half adder, which we discussed in the slide before. So, and doing that, if you move on to the expressions tab, it automatically generates us all these expressions. It automatically draws the k-maps, it minimizes it, and it generates us all these expressions. Now, if we click this build circuit option, we can give a circuit name half adder. So we can also give these restrictions if we want. If we want this logisim-evolution to build our circuit using two input gates only, we can give that restriction. If we just want to use NAND gates only, we can just give these restrictions. But for now, we'll just build a circuit without any restrictions. So you should not use a hyphen in the name. Okay. So on clicking build circuit, it automatically generates as a circuit with all these input pins X and Y, and the output pins C and S. So you can just test it and see it works. So when input is 0 0, the output when X and Y is 0 0, output is C and S are both 0 again. And if we make Y 1, so when the input is 0 1, the output C is 0 and S is 1. So if we make both of these inputs and both of these inputs 1, carry is 1 and sum is 0. And if we make X equals 1 and Y equals 0, again carry becomes 0 and sum is 1. So yeah, this is the thing about half adder. We can just input this truth table into Logisim-evolution. We can carry out all the other stuff like simulating the circuit, building it, everything. So these are like two different representations of the half adder. So the expression S equals xy dash plus x dash y can also be written as S equals x XOR y. So instead of using these NOT gate and AND gate to for this for this CAD for the sum, we can use an XOR gate directly to get the result. So we can also do that. We can implement the same half adder using a different gate system. Okay, these are basically the simulations which we did now. We got the truth table, and we also got the K maps, which can be accessed by going into the minimization section of the. Yeah, and this is the simulation which we made now. And is the expression which we got x dash y plus x y dash and c equals x y. And the good thing is we can import this circuit into another document. We can use this half adder as a block to create even more bigger circuits. We'll learn how to do that later in a second. Now we'll move on to full adder. Full adder, you can think of full adder as an upgraded version of half adder. So it is a combination circuit that forms the arithmetic sum of 3 bits. So in half adder we had 2 input bits. We calculated the sum and carry. But now we have 3 input bits, X, Y, and Z. We can label the inputs as X, Y, and Z, and we can label the outputs as a carry and sum as before. So it has 3 inputs, X, Y, Z, and 2 outputs, carry and sum, C and S. So this is so we can think of this full adder as we studied in binary addition. 2 bits. You can think of X and Y as the addend and the argand bit in the binary addition, and then you can think of Z as the carry from the previous digit. Now we'll see how the truth table actually came. So when all these X, Y, and Z are 0, 0 plus 0 plus 0 equals 0. So the carry is also 0, and it hasn't yet overflowed it. So it hasn't yet overflowed. So the carry is also 0 and sum is 0. So when X equals 0, Y equals 0, and Z equals 1, 0 plus 0 plus 1 equals 1. But we haven't like the sum hasn't yet overflowed, so the carry still stays 0. then x equals 0, y equals 1, and z equals 0. It's the same case as before. The sum is 1, and it hasn't yet overflowed into the next place, so the carry is still 0. So when x equals 0, y equals 1, and z equals 1, we know that 0 plus 1 equals 1, and 1 plus 1 equals 1, 0. Now we can see that our output has overflowed. So if we take the least significant digit of that, 0 is the sum, and the 1 in the MSB, it overflows into the next place, so the carry is 1. So when x equals 1, y equals 0, and z equals 0, the sum is 1 as before, and carry is 0 because it hasn't overflowed. When x equals 1, y equals 0, and z equals 1, 1 plus 0 is 1, and 1 plus 1 is 1, 0. So if we consider the least significant digit, the digit is 0, and as it has overflowed, the carry is 1. So we can, similarly, we can see that when x equals 1, y equals 1, and z equals 0, carries 1, and the sum equals 0. When all x, y, z are 1, 1 plus 1 equals 1, 0, and 1, 0 plus 1 equals 1, 1. So the least significant digit is 1. It stays in the sum, and we can see that our sum has overflowed. We have got an extra digit with 1 in it, so we can consider it as a carry. So in this case, both carry and sum is 1. As we did for half adder, we'll do the same for full adder in Logisim-evolution. We'll see how the circuit comes out. We'll learn how to do that. Okay, now in the same project, you can you can go to the project tab. You can click the add circuit option.
Sandosh, uh,
Yeah.
once again explain the input output part of the half adder. One of the participants is facing trouble. No, not
So
in this, in
yeah, yeah.
logism, combination
So Logisim.
analysis.
Okay, okay.
Tell them how to enter the input variables and output variables.
Okay, okay. I'll do. So if we open the combinational analysis tab in Logisim, if we go to the inputs and outputs tab, there will be like option like this, add a new variable. So if you just click that, you can enter the name of the variable, and you can also choose its size. So if we want to, if you want to add a new variable, let's say z, and we'll have it, we'll keep it to be an 1-bit variable because it can be either 0 or 1. It can just store 1 bit. So you can just click that, you can click enter. It will be added, that's all. And similarly, if we can add an output variable, so if we say if we want to add a new output called maybe out, we can just type the name. We can choose the size. It's 1-bit in default, so we don't have to worry about that. And if we just click enter, so apparently we should not use keywords which we are using in Verilog. So you can think it as some command in Verilog. So maybe you can go over to, yeah. If we just click enter, the output variable will be added. So in the next stage, the truth table will be updated. So we have to, it automatically generates us all the possible combinations here. And we can edit edit the right hand side of the truth table. We can put whatever value we want it to be. And yeah, I hope the doubt is clear. Hello, is the doubt clear?
Yeah, you can go ahead.
Yeah, okay. So similarly, as we did for half adder, we will do the same thing for full adder also. So in Logisim evolution, we can go to the project tab, click on the add circuit option. So to ask a circuit name, you can give whatever name you want to be. We'll name it adderful. Okay, so as we did similar to the stuff we did last time, we can go to the window tab. We can click on the combination analysis option. I'll do this in a new window. So as we can see, the input variables are X, Y, Z. They are like already updated. We can now see the output variables as C and S, carry and sum. Click on this variable. We can click del to delete it. So we have three input variables X, Y, and Z, and two output variables carry and sum. We can move on to the table option. We can the thing is we can change these values to get the truth table of the half adder. So when all these 3 0 0 0 when all these inputs X, Y, Z are 0 0 0, the both the carry is 0 and sum is 0. So when X is 0, Y is 0, and Z is 1, the sum is 1 and carry is 0. So we can just change this column. So when X equals 0, Y equals 1, and Z equals 0, similar to the last case, the carry is 0 and sum is 1. So the entry is correct, so let it be. When X equals 0 and Y, when both Y and Z are 1, the sum is 0 and carry is 1. So we can just click on this, we can change it to 0. And we can move to the carry column, we can change it to 1. When X equals 1 and both Y and Z are 0, the sum is 1 and carry is 0. When X equals 1, Y equals 0, and Z equals 1, sum equals 0 and carry is 1. As the result overflows, sum is 0 and carry is 1. When X is 1, Y is 1, and Z is 0, carry is 1 and sum is 0 like the previous case. And when all of these three inputs are 1, both carry and sum is 1, as we discussed in the truth table before. So we can just click it and change it to 1. Okay. Now if we click on this build circuit option, we can give it a circuit name. And yeah, we got the circuit. So by taking the truth table values as input, it generates this circuit for us with three inputs X, Y, and Z, and two outputs carry and sum. We can test the circuit if you want to. Like we can see whether everything is working perfectly. So when these three inputs, when all these X, Y, and Z are 0, we can see that carry and sum is 0, and we'll make everything 1 next. Yeah, if we make everything 1, we can see that the carry and sum has changed to 1. If we make Z 0, and if we let X and Y be 1, so for 1 1 0, the input the sum equals 0 and carry is 1. We can see that it exactly matches the truth table which we inputted. So this circuit is correct. And this is how we implement. This is how the circuit for a full adder looks. Okay, so moving on. Uh, this is the logic diagram of the full adder which we made. And we can import this full adder as a block with which to use in further circuits. We'll teach that later. We'll look at that part later. Yeah, and now moving on. We'll learn how to implement this full adder. We learn how to implement this full adder using Verilog. So Verilog has I hope you have been introduced to Verilog in the last session. We have explained it. So Verilog is basically HDL. So it is not a programming. It is not a programming language like C or Python. It's a language that is used to describe the design of circuits. It's called a HDL. HDL stands for Hardware Description Language. So it's a language which we'll use to design circuits. Yeah. And to describe a circuit, we can do this. We can describe a circuit in three ways. We can talk about its structure, we can talk about its function, or we can talk about its behavior. So, corresponding to three ways of description, there are three styles of modeling in Verilog. So, we can either do gate level modeling. So, we can either do data flow modeling, we can either do behavioral modeling. In our session, we'll move on with data flow modeling. I'll just explain briefly what everything does. Gate level modeling is like if we have a circuit with a lot of gates like AND, OR, and NOT, there are predefined commands in Verilog which will specify like and will specify the input and output terminals. We'll describe a circuit using gates. In data flow modeling, we'll describe a circuit using the expression which it outputs. So if you want to like describe if you want to like do a full adder in Verilog, if we are doing data flow modeling, we can describe how the full adder works using the Boolean expressions of sum and carry, which we have determined in the previous one. So in this session, we'll model using data. We'll use data flow modeling to design circuits in Verilog. So moving on, let's look at some of the basic Verilog commands which are used to model circuits. First, we'll look at what a module is. So module is a block of Verilog code. It implements a certain functionality. So it's like if you are coding a full adder, you enclose everything within the module and end module keyword. So the whole thing can be imagined as a block, which can be used in later circuits. As we do the code along, these things will get more clear. So if you are not getting it, don't worry. And now let's talk about ports. Ports are basically the input and output. Ports are basically the communication between module and the environment. Which unlock us to the input and output pins of the circuit block we are designing. So there are two types of ports. We can either designate the ports as input, or we can either designate the ports as output. And now, and in this session, we are going to be using data flow modeling. So we'll describe a circuit using the Boolean expression it represents. So we'll use the assign keyword to describe Boolean expressions, and we'll use the exclamation mark operator to represent not. We'll use this two pipe symbol to represent off, or we'll use the double ampersand symbol to represent and. So these things will become more clear if we start the code along. Yeah. Okay, so now we'll move on to EDA playground. We'll code along. I'll explain how I'll explain what every line of the code does, and yeah. So everybody open this EDA playground and we'll start coding this in Verilog. I hope everyone is ready with EDA playground open. So if everyone's ready, we can start the code along. Okay, so let's start this code on part. As you can see, there are two panes in this window. There are we have to write two files over here. So this the right hand side is called the designer.svg file. So it is the code that actually designs a circuit. It actually describes what a circuit is. So the code which will write in the left hand side, the test bench part of this window is the code which will use to test whether our circuit works or not. So on the right hand side, we'll describe the design of the circuit. On the left hand side, we'll write the code to test the circuit and like see if it actually works. Okay, first we'll start the design part of the circuit. So the first line is module. First, we have initialized a module called full adder. As we have seen, everything in Verilog is enclosed within modules. So we have just initialized, we started a module named full adder. And the things in the brackets, the S, C, X, Y, and Z are the input and output pins of this module. And notice, don't forget the semicolon at the end. We start a module, we use an end module command to end it. And the actual code that describes the design goes into the place between module and the end module. Okay, now the things in the bracket, the S, C, X, Y, and Z, they are the pins of the module. So the next job of us is to we have to like tell the compiler which pins are output pins and which pins are input pins. So I'm assuming that S here stands for the sum pin which we consider the output. C here stands for the carry which we consider the output, and X, Y, and Z are the input pins. So in the next line, we have to like tell the compiler. We have to tell the compiler which pins designate input and which pins designate output. So we'll do that now. We'll use the output command and the input command. Okay, so this line basically what it does is it tells the compiler that the pins S and C are going to be outputs, and this line tells that the pins S, X, Y, and Z are going to be inputs. Now the next thing is we'll use the assign keyword. We'll type a Boolean expression. I hope you remember the Boolean expressions which we got for the full adder and half adder. We can just use the assign keyword. We can assign those expressions to the outputs S and C. So first, we'll consider carry. So the expression for carry is, as you've seen, the expression for carry is xy plus yz plus xc. Yeah. So we can type this Boolean expression over here using the logical operators which we discussed. So x and y, and is represented by a double ampersand like this, which represents Boolean or we can use a double pipe symbol to represent the plus symbol. And don't forget the semicolon at the end. So this is the Boolean expression which we derived before. C equals xy plus yz plus xc. So the and is represented, the and between x and y is represented by this double ampersand symbol, and the or in the expression is represented by this double pipe symbol. And we can do the same thing for the sum also, but it's a bit longer. Bear with me. Okay, the expression which we derived for sum is x dash y dash z plus x dash y z dash plus x y dash z dash plus x y z. We can just enter this into Verilog. we can do it term by term. We can do that term by term. Okay, first we'll do that xyz term. I'll also comment these expressions here so that we can do that easily. So the double the thing I've written after the double slash is called a comment. It doesn't affect the program in any way. We are just writing this for a reference. So it doesn't affect the run of the program in any way. Okay, so this is the expression which we got for this is the expression which we got for the sum of the full adder. The second term here is the term here x dash y dash z. Uh, the exclamatory mark before x represents x dash. The double ampersand operator represents and similarly the ampersand before y represents y dash, and this double ampersand represents z. So the overall term in this bracket is x dash y dash z. And yeah, so this is the expression which we wanted. Uh, the third term, you can see this x dash times y times z dash. It's the third term, x dash plus y times z dash over here. And the fourth term, x dash y z dash, can be represented like this: x dash times y times z dash. Okay, so this is the expression. This is the Boolean expression which we found out for the sum and carry, and we are done with the design part of this code. So we are done describing a circuit. We have done describing what are the inputs. We have done describing what are the outputs, and we are done with describing how the outputs are related to inputs using the assign keyword. Now we are ready to test our circuit using test bench code. So the code in the left part of the session is called the test bench. So this code is used to like test whether our circuit actually works. It does it give the required output. So now, similarly like the last case, we can just start creating a module like this. We can just start by creating a module. Name it however you want to, like starting module. You can end it. So the all the code we write for testing this circuit, they come between the space in the module and end module. So yeah, the next the next thing we have to do is we have to initiate the inputs and outputs. We have to initiate the inputs and outputs like we did in the last case. But we don't use the input and output keyword for that. There are some different keywords here. we use the reg keyword. We use the reg keyword to tell what are the inputs here. So let's name it x1, y1, and z1. I'll explain why x1, y1, z1 in a second. Just bear with me. And then we use the wire keyword to represent what the outputs of the circuit are. So we use the reg keyword to represent the to initiate the inputs of the circuit, and wire keyword to represent the outputs of the circuit. And then the next thing we have to do is we have to call this design. We have to call the module which are created in design file as a. You can think of it like a function call. We are like calling this module full adder over here, so that we can test it. So this calling of a function is called instantiation in Verilog language. So this is the name of the module full adder we have created. So we are just calling this over here. I'll just explain this line in a minute. First, I'll just type it. This line is called an instantiation. So what you've done is we have actually called the full adder. We have called the full adder module which we have created in this design.sv file. We have just called it over here full adder, and we can just name it anyhow we want to. And in this case we have used the same name, but that's okay. And now these inputs. Uh, So you can think of actually connecting. You can think of connecting uh, x1 and x. You can think of connecting it. You can think of this statement as telling that x1 and x are connected, y1 and y are connected, z1 and z are connected, c1 and c are connected, and s1 and s are connected. So the x, the y, the z, the x, and c outside the brackets, they all come from the ports of this module full adder which was created over here. And the stuff inside the brackets, the x1, y1, z1, c1, and s1, they come from uh, the stuff which we initialized in this module. So this is the format to initialize. This is the format to call a different module into a test bench code. So this is how we do it. Yeah, and then we use this command initial. I'll explain what it does in a minute. Yes. So the initial keyword is a keyword. It has a block of statements into it. We can enclose a block of statements within the begin and end part of the end keywords of this initial block. If we just give a block of statements in that, so whenever this test bench code is run, whenever the program starts execution, the code present in the initial block, it also starts to get executed. So if we just want to print the output values of the circuit, we can put it in the initial block. So as soon as the code starts running, we'll start to get the we'll start to get the outputs of the full adder. Okay, now we'll use this command. This is called the monitor command. So this monitor command is a command which is used to print the outputs and inputs of the circuit. it's a special kind of print statement. Whenever the inputs change, it prints it. So we just want to print the values of inputs and outputs. We'll give x1, y1, z1, 1 and s1. So whenever as soon as these inputs and outputs change, we'll get these values printed in the the output console in the bottom of the screen. Okay. Now we are ready to give some inputs to the full adder, and we need to like see what the outputs are. And what it does in a minute. Okay. So these three lines, we are actually giving the inputs to the circuit which we are testing. So x1 equals the one in the front represents we are giving an 1-bit input. We are just giving zeros or ones. We are just giving an 1-bit input. So we just put a 1 over here, and there is this single code symbol over here. And after the code symbol, there is B0. So the B0 represents that we're B0 represents the binary, the binary form of the value 0. So this statement basically means that we are just giving 1 bit of the binary form of 0. So it basically means that we are just giving 0 into x1. So similarly, the same statement here means that we are just giving zeros into y1, and we are just giving zeros into z1. And this #1, it means we are just delaying the operation of circuit for just one time unit. And after delaying this, we are again changing the input variables a bit. So we're just letting x1 to be 0, y1 to be 0, and we'll just change a bit over here. So the B1 means that we are considering the binary form of the value 1, and we are just giving 1 bit of it. It means that we are basically giving 1 into the circuit. So in the first case, as soon as it starts, the input variables will be 0, 0, 0, and after a delay of 1 time unit, the input variables will be 0, 0, 1. And this monitor command, it can be used to like print the input and output variables like this. So now we are done with the test bench code of this test bench code. We can move to the tools and simulators part. We can click this drop down. We can select Icarus Verilog 0.97. This is the compiler. You can think of this as a compiler which we are using to run this code. Yeah, after saving this, we can go to this log screen. We can click run. If we find any errors in the code, it will show here. And if we don't find any, it will just print the outputs. So now there are no errors in the code. We got the outputs. We'll actually try to understand how these outputs come from. So we have used this monitor command with x1, y1, z1, c1, and s1. So it prints. We instructed it to print 5 values. So it prints all the 5 values. So in the first case, we gave x1, y1, and z1 as 0, 0, 0. So it printed. That's the reason for these first 3 zeros over here. And the c1 and s1 represents the value of carry and sum. If you remember the truth table, we can see that whenever when all these three inputs are 0, both the carry and sum are 0. So it prints C as 0 and S as 0 here, which means that our full adder is working properly. Now if we move on to the second line, our inputs are 0, 0, 1. X1 is 0, Y1 is 0, and Z1 is 1. So these are the inputs 0, 0, and 1. So as if you remember the truth table, we know that when X is 0, Y is 0, and Z is 1, carry is 0 and sum is 1. So carry is 0, so that's the reason for default 0 over here, and sum is 1. That's why we get 0 over here. So yeah, we are done with the code along part of this Verilog, and it's a good time to take a break. We'll meet after 5 minutes.
Okay, is my voice audible?
Yeah, you're audible.
Yeah. Okay, then we resume our session. Okay. Hello everyone, myself Irvin from Electrical 21. Now I'm going to discuss about three more combination circuits, namely comparator, decoder, and multiplexers. Okay, start. I hope my screen is visible.
Yeah, it is.
Yeah. Okay. In this session, we are going to like we have done a one-bit comparator and how to compare one bit of two numbers. In this, we are planning to build a three-bit comparator in which we are going to get three inputs, like two binary numbers. Each binary number has three inputs, like three digits. So we are going to get six inputs in total, and going to give three outputs. Same as the outputs are same as that we have done in one-bit comparator. Okay, this is the one-bit comparator we have done yesterday. But we have to do one more thing. We need to add a enabler, which is a switch. Uh, like if the enable is zero, then everything like we are going to off the entire circuit. The off I mean is like every output should be zero, irrespective of what values of A and B we are going to input. Like C, yeah. In okay, in this, for the case when where enable is zero, A and B, irrespective of all values of A and B, every output is zero. In case if enable is one, then the values of A and B like X, Y, and Z corresponds to that we have done in the yesterday's session. Now let's see how are we going to add this enabler. Okay, this is the one-bit comparator that we have done yesterday. Now open a new circuit and come back to it. Like change your mouse cursor and like select everything, copy it using Control C and paste it here. And go over there once again. And go over there. Right click over this untitled. Press Add Circuit. Enter one-bit comparator. Like bit comparator. One. Enter it. Like make sure the search like the search class is in this one-bit comparator circuit. Now go over there and paste the circuit and press over the and right click here to set this as the main circuit and right click over the main and remove it. We don't need it. Okay. Now the circuit is like then we copied the circuit we made yesterday. Now we are going to add the enable part. Add a input. Double click over here and enter the variable name enable.
Sir, please, can you repeat once again?
Yeah. Like which part do you have down?
That I unable to get this one-bit comparator.
Okay, unable to.
This untitled, below the untitled, I unable to get this one-bit comparator.
Okay, one-bit comparator. Just go over like place your mouse cursor over there, like over the untitled. Right click. We'll have the add circuit option. enter one bit comparator and click OK. I hope your doubt is clear.
Circuit name I
Like-
need to. Circuit name
Yeah.
I need.
Yeah, you need to give.
Okay.
Just
okay.
type it as bit comparator 1. I guess
Okay.
you can't type 1 in front of the variable, like circuit name. Okay, I will continue. Now, add 3 AND gates. I will explain why are we adding AND gates later. And for the other input for the AND gate, just connect the enable to every AND gates. And click every input terminal and give it as A. And for this, give the name as B. And this is the input terminal correspond to A is greater than B. So we are going to give it as X. This is for A equal to B. I'm going to give it as Y. And this is A less than B, which is Z. Okay. Now go save your circuit. Now your circuit is saved. I hope you understand it. Now I'm going to tell why we added those. Okay. Just a minute. Okay. Okay. Now I'm going to tell why did we add those AND gates. I hope you all remember the properties we discussed in first class, like F and 1 is F and F and 0 is 0. In case the enable is going to work as normal. So if enable is 1, every AND gate has 1 as in one of its input, and the other variable just get transmitted without changing anything. So we are enable 1 just acts as a normal mode. In case if enable is 0, like 0 and F and 0 is always 0. So irrespective of what the other value of the input, we are going to get 0 at every 0 as the output for every AND gate. So the circuit will get like we are turning off the circuit. I hope the logic is clear. Now moving on to the 3-bit comparator. Okay, now we have built the 1-bit comparator. 1-bit comparator. Now we are going to use this 1-bit comparator to make a 3-bit comparator. Now, what is a 3-bit comparator?
आपको मिल रहा हूँ मेरे पास जितना भी आया है आपको पूरा फॉरवर्ड करता है आप उसको डिपार्टमेंट डायरी रख लीजिए
Can you mute please? Okay. Okay. What's an 3-bit 3-bit comparator? We are just comparing 3 numbers. That's all. Like what we'll be doing in comparison, the algorithm of the comparison process. In case of decimal numbers, we will always start with the most significant bit or the highest digit. We will compare these two numbers. Here you can clearly see that 8 is greater than 7. So the process ends immediately here. So this number is the answer. This is the greater one. Similar logic can be applied to binary numbers. In binary numbers, we are same to decimal. We are going to compare first compare the MSB. Here 1 and 0. Since here 1 is greater than 0, that is A2 is greater than B2. Our process ends here immediately. So in this case, A is greater than B. Coming to the second case, where the MSB are equal. In this case, we are going to move to the next bit set of bits. Here you can clearly see that the B bit, that is B1, is greater than A1. So the process ends here immediately. So A is less than B. Similar logic goes for these two cases. In this case, these two set of values are equal. We move to here. These two set of values are again equal. We move to the last set, the last bit, LSB, least significant bit. Here, the least significant bit is also equal. So in this case, since the every digits are equal, we are going A is equal to B. Similar logic can be applied for this. Now we are going to, I hope the logic is clear. Now we are going to build the 3-bit comparator in Logisim. And before that, to Logisim, create a new window, and same step. Just go over this untitled, add a circuit, name it as comparator. Comparator 3-bit. Enter. Now, as we discussed, we are going to have two 3-bit binary numbers, which means we are going to give 6 inputs. Mark the first input as A2, the next one as A1, A0, B2, B1, B0. Okay. Now, as I mentioned in the the drawings, we need to have three single bit comparators. We are going to compare every individual bit bitwise. Okay. Before that, set this as your okay. Set this as your main circuit and remove main. Now we are going to I'm going to show you how to import the 1-bit comparator we have built earlier. Just go over the project icon, the project option, drop down, and you will have the load library option. In this, click Logisim-evolution library and select the 1-bit comparator we just now built. Okay. The 1-bit comparator will get added as a library. You can see it down here. I'm now going to use this. We need 3 comparators. 1, 2, 3 for 3 individual bits. Now I'm going to tell you why did we actually added the enable option to our 1-bit comparator. First, let's connect the A and B to corresponding to the comparators. Connect A2 and B2 to first comparator. Make sure that you connect to A and B input of the comparator. Again, connect A1 and B1 and connect B1 like A1 and A0 and B0. Now, as we seen here, we are going to check for the another circuit only if the previous bits are equal. Like in this case, A2 is equal to B2, 1, 1. So if like y is like I told you earlier, y is for A is equal to B condition. If it's true, we are going to activate the next enable of the next bit. Similarly, doing it for the next bit. Now, if all bits are like so all bits are activated and the last bit gave A is equal to B condition, then our output will be A is equal to B, like both numbers are equal. I'm going to use the same variables as we used in 1-bit comparator. Actually, this output is for A equal to B, so I'm marking it as Y. Okay. Now take an OR gate and in left side you will get an option of the features of this OR gate. Go over there, change the number of inputs to 3. Now connect all X output of from the 1-bit comparator to this or as an input to this OR gate. Take another OR gate and do the same thing. Make the inputs 3, enter, and connect all Z's to the OR gate as an inputs. Okay. Now the Z's OR gate correspond to A less than B input. So name it as Z. And name this one as X. This output corresponds to the output for A greater than B. So name it X. Now our okay. Now we have forgot one more thing. We need to enable this 1-bit comparator, irrespective of what the situation. So I'm giving it a constant one. Just a minute. Okay. Is my screen visible?
Yeah,
No.
it's visible.
Yeah, okay. Okay. Now this is the circuit I built earlier. I guess I made some connection mistakes. I will send the circuits after this session to you guys. So now our comparator is ready. Now we are going to see whether in this case all the inputs are 0 0. They are also 0 0. So A equal to B, the output gets light up. See, you can see this one, others are 0. So if I input A as 1 1, which is clearly greater than B, A greater than B output gets lit up. As you can clearly see, and for A I gave 1 0 1, and for B I gave 1 1 0, which means B is greater than A. You can see A less than B, like B greater than A, output gets lit up. So our 3-bit comparator is ready. You have any doubts, you can ask. If not, let's go on with decoders. Comparator, you guys can try it out using Logisim. This is the truth table. You can go input it and build circuit. We'll send this slide after this session. Don't worry. Decoders. In decoders, we are going to give inputs, and corresponding to each input, we are going to output the minterms. I guess you guys have learned minterms in the last session. Here in truth table, you can clearly see 0 0 corresponds to minterm M0. So D0 here represents the minterm M0. So in 0 0 only is 0. In rest other cases, the output is 0. Similar goes for D1, D2, and D3. Now let's build it using Logisim. Now go over there, click New. Add circuit, decoder 2 by 4. Enter. Set this as your main circuit. Remove the main circuit. Now right click over here, go to analyze circuit, enter the inputs. Inputs are X, Y, and X and Y. Outputs are D0, D1, D2, and D3. Now build the circuit. Now go build the circuit. Untitled to circuit name decoder 2 by 2. Check it once and click OK. Yes. And enter the truth table. In truth table, okay. Now enter the values in truth table. For D1, only X0, Y0 should be 1. Rest all should be 0. For D0, X01 should be 1 and rest should be 0. So 0, 1, 0, 0. For D2, it should be 0, 0, 1, 0. D3, 0, 0, 0, 1. Now go hit the build circuit. Create a new project. Name your circuit as decoder 2x4 and click OK. Now the circuit, we have built the circuit successfully. Now go over there, set it as main circuit and remove the pre-existing main. Now let's change the appearance of the circuit. Now this is the block diagram. We can customize the circuit however we want. For this decoder, you can like change the scale and size of the box by clicking over the corners and move it by clicking over the sides, the black color line. Now place the inputs. If you click, it tells us the port X and this is Y. This is D0, D1, D2 and D3. You can also name it however you want. But this is a 2x4 decoder. You can also move the text. Now we can go and save it. Okay. This is the logical diagram of the 2x4 decoder we have made. And with similar logic, we can also build a 3x8 decoder. I will show you. I already built it. So yeah, you can also go there, enter the inputs as XYZ and output from D0 to D7 and enter the truth table and click build. You will get a decoder circuit like this. Okay. I hope you understand the decoder part. If you have any doubt, you can ask.
Hello.
Hello.
Yeah. Okay.
Yeah.
How did you generate the block diagram?
Okay. Which block diagram? Oh, block diagram. Okay.
Yeah,
Okay.
2x4 decoder. Yeah.
2x4. Okay. This is the okay. You are here, right? Go over there. There is a like a box diagram. If you go over there, it says as edit the viewed circuit appearance. If you click there, the block appearance of the circuit will come. You can customize the circuit however you want. Did you get it?
Yeah, but like when I was reshaping this rectangle part, like the blue dots are going out of that rectangle box.
Okay, we can change it. It's up to us.
Okay.
Okay. If you have no doubt, I can go.
Yeah.
Yeah. Like think it as an select line. Depending upon the values of X, Y, Z, the corresponding outputs will get activated. you can clearly see in the case of x, y, z all being 0, the decimal value, it represents 0. So D0 will get activated in this case, and rest will be 0. For 001, D1 will get activated and rest will be 0. So it's more like an, what to say, it's an select line. If you don't understand the name of the the decoder, you can remember it as a select line. Okay, moving on. Now this is the diagram. You can use it for future purpose. Going on to multiplexers. In combinational circuit, multiplexers is a switch-like thing. Depending upon the control values from S0, S0, S1 up to Sn, depending upon these values, we will select the output. It's more like an gear. Depending upon what gear you put in your car goes in different speed range, right? For different speed range, you will put different gears. You can think it as that. Okay, this is a simple 2:1 mux. In this, depending upon the value of s, if s is equal to 0, then the output will be connected to a0 directly. If s is equal to 1, then a1 directly goes to output. It's more like a switch, like changing the lines. In switch, we only have like 2 on or off, but we can have more than 1. Like in 4:1, we can have 4 different modes. If you have any doubt, you can ask for multiplexer logic. Okay, if no doubts, I can carry on. Okay, like in 4:2 mux, it's similar to that of 2:1. Like in 2:1, there are only one control line. Yes, yes. For one, we can only have 2 different values, 0 and 1. So we can only have 2 different modes. But here, since we have 2 control inputs, we can go up to 4, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1. Okay. This is the truth table for 4:1 mux. If A is equal to A and B are both 0, then output will be directly connected to D0. Similarly, we can say for other 0, 1 corresponds to D1, 1, 0 corresponds to D2, and 1, 1 corresponds to D3. If I give input as 1, 0, then the circuit will automatically connect D2 to the output Y. Okay, now we are going to simulate it using 2x4 decoder. As I said, that decoder is more like a select line. Now we are going to build it. Okay, is the screen visible?
Yeah, it is.
Yeah, okay. Now is the simple 2:1, 4:1 mux using that 2x4 decoder we have built. Okay, I loaded the library similar to what we have done. Now we can clearly see, depending upon the value of S0, I clearly mentioned that if both are 0, D0 will get activated. Other lines will be 0. And we have seen the property, like we use the enabler in 1-bit comparator, right? If the value of if the AND gates input is any one of the input is 0, then other will the output will always be 0. So in this case, only D0 will get like D0 is 1. So this AND gate will only give the value. All the AND gates will give 0. And talking about this AND gate, the other input we get from I0. I0 is nothing but the different mode of lines we used in decoder, like in the mux. Like in the diagram, we mentioned it as D3. You can name the variable however you want. So I'm naming it as I0, I1, I2, I3. If S0, S1 is 0, 0, then D0 will get activated. And this is the only valid AND gate. Depending upon the other value of input, if we go over there and give it as 1, the 1 will get directly transferred to the output value. If I change however I want, the other AND gates will be still remain 0 because they are not activated. Similarly, by changing this, if I change S1 to 1 and S0 to 0, this value corresponds to the I2. In this case, only as you can clearly see, the green line gets activated in the third AND gate, which corresponds to I2 value. The I2 value will get directly transferred to the value of the outputs. Like if I enter whatever, like change the other values, it won't affect our output because only I2 is activated. Rest are not. Like it's connected to I2. You can remember it as like that. Okay. If you have any doubt in mux, you can ask. Like in how did the circuit works using decoder? You can unmute and ask. Okay, if you have no doubts, then Santosh can take the Verilog part. Okay, since we ran out of time, we are not doing the Verilog part. We will be sending the slides. You can see it, and also I will send you a Google Drive link of all the circuits I built, so you can try it out.
Excuse me.
Yes.
Could you explain the enable part once again? Like, I didn't
Okay.
quite
Enable of
the
which one?
comparator in the comparator.
Comparator. Okay, I will explain. Okay, can you see the screen?
Yes.
No, comparator. Okay. Okay, in enable part. Okay. Say the case where enable is 0. In this case, for these 3 AND gates, one of the input is always 0. Like this input is 0, this is 0, and this is 0. What happens if one of the input in of the AND gate is 0? The output will be definitely 0, right?
Yes.
So this is an off situation where every output will be 0, irrespective of what values it change.
Okay, so
See,
the working of
values go.
comparator is like this. Like there will be an AND
Yeah,
gate.
working of a comparator. Yes.
So like you were saying that enable pin is like used when we are changing the values of A and B, something like that.
No, not changing values exactly. Like I'm adding a switch to the comparator. We don't want our comparator to be on all the time, right?
Yeah.
We only want it to be on whenever we want to. So
Yes.
we are adding an enabling pin.
Okay.
So in the 3-bit comparator case, you can clearly see that. Okay. This is not working. I will show the. In this case, the first comparator will compare the circuit.
Yeah.
If the circuit, like if first we are comparing it, right? If in the first MSB digit itself, we can clearly see that one is greater than the other, we can end the output. We don't want to move to the next comparator.
Yeah.
If in this case, if B2 is 0 and A2 is 1,
Yes, it'll end at the
like in
first
this
one.
case, end it in the first out. So I'm not activating these two AND gates. These two 1-bit comparators. So our output will be directly given by this 1-bit comparator.
Yeah.
I only want them to be active if the first 1-bit comparator gives an A equal to B output. Like if both of them are equal, then only we move to the next bit.
Yes.
In all other cases, we will end it there. It's
Yeah.
like it's the algorithm of the 3-bit comparator. We'll compare everything bitwise and move to the next bit if and only if the 2 bits are equal. Like in this case, both A1 and B1 are equal. So this comparator will give will lit up the A is equal to B output. So this output will be directly activate this comparator. That's why I connect A is equal to B from this to enable of this one.
Yes.
So it compares again and checks if in this case A0 and B0 both are equal. So it again like the output of A is equal to B gets high value. So A is equal to B is 0. If I change A0 to 0 and B1 is 1, then A is less than B gets activated and A less than B. Here you can clearly see it gives value 1. All the other are 0.
Yeah.
That's how it works.
Yeah. Yeah. Thanks. Like, what is the task for today?
Yeah, we will send the document, the PDF
Yes, sir.
for the task.